So the important concept when we want to think about why it is that things rotate is actually thinking about the idea of torque. The first question is, well, what on earth is torque? And so let's start by thinking about just a simple bar here. So here's a bar, and I'm going to exert forces on this bar, and what we want to do is think about how those forces relate to this concept of torque. So the first thing that we'll need to do is we'll need to define a pivot. And the pivot is simply the point that an object rotates around. In a lot of situations where we haven't intentionally pinned an object, the pivot's just going to be the center of mass. But I could just as easily say, oh, well, I'll choose to pin this bar so that it rotates around this end, or that end, or some point that's not at its center of mass, or whatever it is. So the pivot's simply going to be the point that the object rotates around. So if I take a force and exert it at the pivot, well, I don't expect that that force is actually going to make my bar rotate. Right? It'll just push against the pivot will hold it in place, and so I don't actually expect that force to do anything. But if I exert a similar force, so same magnitude, same direction, but do it a little ways away from the pivot, then in this case, sure enough, I expect that this is going to make my bar rotate, in this case, counterclockwise. So as I push down on the right side of the bar, I expect that's going to make the bar start to rotate in a clockwise direction. If I exert a third force that's actually all the way out to the end of the bar, then again I expect that that will make the bar rotate even more. So I'll get a larger rotation, larger change in how the bar is rotating. So initially it's at rest. It's going to end up with a bigger rotation at the end if I exert that same force all the way out in the end. So torque is a measure of how much a force acting on an object causes it to rotate, or causes it to change how it's rotating. So as I moved my force from the pivot to a little ways out to further out, I got a larger and larger torque because that same force was going to end up causing the bar to rotate more as I moved it further away. So what else does torque depend on? Well, we started by saying that equal forces in different places is going to give me a different torque. So one of the things it clearly depends on is the distance from the pivot. Another thing is, well, I could have a different magnitude force. So notice here I've got a small force acting on this end of the bar, a large force acting on this end of the bar. I don't expect their torques to be the same, even though they're both acting the same distance from the pivot. I expect the larger force to be able to exert a larger torque. So sure enough, the magnitude of the force affects how much torque you generate. I can also take that same magnitude force, right? So F5, my fifth force here has the same magnitude as F3. It's acting at the same point as F3, so both of these are pushing on the end of the bar. But you'll notice that it's not oriented in the same way. So it's pointing off at this angle, sort of a glancing blow, if you will, on the bar. And so I don't expect it to generate as much torque as what F3 will. So the relative orientation of the force that's pushing on the bar, or pushing on my object, that'll also affect how much torque it generates. And then again, so if I think about that same magnitude force, well, there's a relative orientation I could give it. So force 6 has the same magnitude as force 5, and 1, and 2, and 3. It's acting at the end of the bar again. But you notice that here, this relative orientation, I don't expect it to actually generate any torque at all. It's not going to cause the bar to rotate clockwise or counterclockwise. It's basically just going to push against that pivot. The pivot will hold it in place. So in the same way I said I don't expect force 1 to generate any torque, I don't expect force 6 to generate any torque. So there are 6 forces here, 2 of which we said don't generate any torque because they're either acting at the pivot or directed directly towards the pivot. We said my magnitude can change how much torque. The relative orientation can change how much torque. Well, the last thing that should be pretty clear here is that force 2, force 3, force 5, these are all trying to get the bar to spin clockwise, right? So you push down on the right-hand side of the bar. That's going to try and make it spin clockwise. You push up in some way on the left-hand side of the bar. That's also going to try and make it spin clockwise. But force 4 is actually going to try and make the bar spin in the other direction. It, in pushing down on the left, is actually trying to make the bar spin counterclockwise. So the last thing that torque depends on is, well, what's the direction that the force is trying to force the object to spin in? And so how do I encapsulate all four of these things into a simple mathematical equation? And it looks like this. So here, tau, the Greek letter tau, is my torque. And again, the Greek letter here, as in the same way that we talked about with our rotational motion variables, we're using Greek letters to talk about the fact that we have rotation. Well, we use tau for the torque because, again, this is something that's very much involved in rotation. Torque is trying to change how things rotate. I calculate the torque with a cross product. So R cross F. Well, the force F, that seems clear, but what on earth is R? So R is actually it's the position vector for your force. So for each force, you can draw a vector running from the pivot to where the force acts on the object. So if I think about force 1, since it acts at the pivot, the R vector for force 1 is just the 0 vector. Plugging in the 0 vector here tells me why force 1 generates no torque. Plugging the 0 vector into a cross product, you're always going to get back 0. F2, there's its R. And so notice that it points to the right where this force acts. It's not very far away, right? It's a relatively short distance. Whereas if we think about what's going on for R3, right, the position vector for the third force, it's much longer. So again, here we've got two forces that are the same, but by making this position vector longer, we've generated a larger torque. So this equation basically is going to capture all the information we need in terms of calculating a torque. So torque is a vector. It is defined by a cross product. So cross product, we said, was our way of multiplying vectors together to get back a vector. And so I've got my position vector for the force. I'm going to take the cross product of that with the force itself. That's what's going to calculate the torque for me. One way to do that, so our process, is simply our rule for doing a cross product, says you take the components of your vectors, your x and y components. So we're just going to deal with position and force vectors within the xy plane. And so the cross product of those, one way to do it is just use my rule that says it's going to be the x component of r times the y component of the force minus the y component of the position times the x component of the force. And you notice the k hat tells me that this is actually going to end up being in the z direction. So if I have forces and positions in the xy plane, my cross product is always going to be perpendicular to the plane defined by r and f. And so if r and f lie in x and y, then the torque has to be in z. And again, what the torque, the definition or the direction of that torque is basically lying along the line of the axis of rotation. So when we talk about things forces that exert torques that try to make an object spin clockwise or counterclockwise, well, the clockwise or counterclockwise are all, both of those are trying to rotate about an axis that points into and out of the page. So that's why they rotate clockwise and counterclockwise. So the torque will either rotate out towards us, point out towards us, or point into the page. Both of those are in the z direction. So this is one way we can calculate the torque. And basically the nice thing about this is, certainly at this point in the semester, we're very good at breaking up vectors into components. So this is easy to say, hey, if you can break up these two vectors into components, then you can go ahead and calculate the torque. by simply multiplying those components together in the right way. The second way we can calculate the torque is, well, for any cross product, the magnitude of the cross product is going to be the magnitude of one vector times the magnitude of the other vector times the sine of the angle between them. So the magnitude of the torque is going to be the magnitude of the force times the magnitude of that position vector times the sine of the angle between those two vectors. Now notice this just gives us a magnitude, and we've said torque is a vector, so it needs not only a magnitude but also a direction. So there's a right-hand rule that we'll be able to use, that we'll talk about in class, to figure out the direction of the torque. So notice this one, our method 1, automatically gives us a direction. This quantity will be either positive or negative, so I'll tell you whether it points in the positive z or negative z direction. We're going to need a right-hand rule when we do it this way to tell us whether it points in the positive z or the negative z direction. What are the units of torque? Well, again, if I think about sort of this expression here in method 2, then torque's going to have the units of force times units of position times the units of sine of an angle. Well, sine of an angle is just a number. Units of force are newtons, units of position are meters, so units of torque are newton meters. And we've run across this unit before. We ran across it in terms of work and energy, right? We said, oh, work we can think of in certain situations where we have a constant force is going to be force times distance times cosine of an angle. So that also had the same unit. But one of the things that's very important to remember is that torque is always newton meters. It's never J. So we're never going to use an energy unit as shorthand for a unit of torque. We're always going to write out torque as newton meter. The other thing I can come back and think about in terms of my method 2 here is this magnitude of the position vector times sine of the angle between these two vectors actually tells me what my moment arm is. And so torque, one way to think about the torque, or another way to think about the torque, is to think about, well, it's going to be the force, magnitude of the force, times this moment arm. So that's also going to give me what the torque is. And so the next question becomes, well, how do I calculate what the moment arm is? And so to talk about the moment arm, we've actually first got to talk about the line of action. So basically the line of action, again, action is just our Newtonian word for saying force. So if we think about the 6 forces we had acting on our bar, the line of action for each of these forces is just what's the line that that force lies along. So for force 1, here is its line of action. For force, the moment arm is the perpendicular distance between the line of action and the pivot. So you notice force 1, the moment arm, or the line of action runs through the pivot. This tells us that the moment arm is 0 for force 1. So you take force 1, you multiply it by a moment arm of 0, again that gives you 0 torque. So this confirms what we talked about earlier, that force 1 generates no torque on our bar. Force 2, on the other hand, here's its line of action. The perpendicular distance between the pivot and the line of action happens to be this distance for force 2. So I could get the torque generated, the magnitude of the torque generated by force 2 by taking the magnitude of this force times this distance. Force 3, here's its line of action. So the perpendicular distance to that line of action is this entire half of the bar, half of the length of the bar. So again, we can easily see here that force 3 will generate a larger torque than force 2 simply because it has a longer moment arm. The longer you make the moment arm, assuming you keep the force the same, the larger you're going to make the torque. Well, let's think about force 5 for a minute, because it's, again, pointing at an interesting angle. And so what you'll notice is that force 5, its line of action lies like this. And so the moment arm for this force, again, it's the perpendicular distance to the line of action. So the moment arm for force 5 doesn't lie along the bar. It actually lies off the bar, and it happens to be this distance. And again, it's easy to see here that this is why force 5 exerts less torque than force 3. They're the same magnitude, but because of the way you have tilted that force, you've got a line of action that gives you a shorter moment arm, and so you generate less torque. If you think about force 6, again, notice its line of action runs through the pivot. So its moment arm is 0. So again, we've got a situation where the torque is 0 for force 6 because it has 0 moment arm. So two conclusions that we can draw from this in terms of thinking about the moment arm and the line of action and how that tells us what's going on with the torque. First thing is what we deduced from force 1 and force 6. If the line of action runs through the pivot, then the torque exerted by that force on the object is 0. So that one's just anytime you see the line of action for your force running through the pivot, you know it generates 0 torque. The other thing you'll see is that you get the maximum amount of torque when the moment arm is as long as possible. So again, we said if I take this force, even though it's as large, same magnitude as this force, because of the way that it's tilted off at this angle, it's going to give me a shorter moment arm. So to get the maximum amount of torque, I actually want to swing force 5 around so that it's pointing up. Because now that's going to make my line of action run vertically, which means I get the moment arm to be this entire half of the bar, or half of the length of the bar. So I maximize the torque when the moment arm is as long as possible, which means that the angle between the force, so if I rotate F5 around so that it points up, right, my force points up, R points from the pivot to where the force acts, it's going to point horizontally. And so something pointing vertically and something pointing horizontally, the angle between those is going to be 90 degrees. So your torque is as large as possible when the angle between your force and the position vector for that force, the vector running from the pivot to where that force acts, is a 90-degree angle. We can sort of extend this second idea a little bit further, because basically what it tells us is that only the component of the force perpendicular to R exerts a torque. So part of what's going on with force 5 here is the idea that it doesn't exert as much force as it can, because you basically have a component that pushes perpendicular to the bar. Perpendicular, right? That's going to be perpendicular to your position vector, right? Your position vector here is going to point from the pivot out here to the end of the bar, so it's going to point to the left. So there is a component of force 5 that is perpendicular to that generates the torque. There is a component of force 5 that lies along the line of R that generates no torque. So the reason that the torque generated by force 5 isn't at its maximum is because you have this component that doesn't help exert any torque. And so if you want your torque to be at a maximum, you want the whole thing to be perpendicular. You want your entire force to be perpendicular to that position vector so that your torque is as large as possible. So this is what torque is. Again, it's trying to tell us how forces act on objects to change their rotation, and we'll build up from this in terms of thinking about our rotational motion in class on Monday.